Welcome to the final session on complex numbers, sketching subsets on the complex plane. It's a particularly important unit to finish with. So what is it about? So as we know, any rule between two real variables, x and y, can be graphed on the Cartesian plane. When we use a solid line to represent a curve on the plane, it actually indicates infinitely many points, x-y combinations smashed together, each of whom satisfy the given rule, matching that particular curve. Okay, let's have a look at some examples. Okay, you can see before you a couple of very common curves, the parabola and an exponential curve, a member of the exponential family, and their associated rules. Now, have a look at, I've got those rules with set notation, collecting all the ordered pairs x comma y, such that y is related to x in the manner described. We drop the set notation for convenience, but in fact, that's what we're doing when we're sketching. We're collecting all the xy pairs that match the rule, representing them as a solid line because each of those are densely packed together along that particular line. Now, the natural question is, can curves be described on the complex plane? And the answer is yes. However, not in a relationship, in the same relationship that you're familiar with in the Cartesian setting, in quite a different kind of setting indeed. So sketching on the Argand diagram is not in terms of this Cartesian relationship between your x and your y, but rather it's in terms of set notation. That is the set or locus, as it's more correctly termed, of complex numbers that is subject to a condition. So we're going to look at all kinds of conditions that give rise to particular sketches on the Argand diagram. Okay, so we're first going to begin by exploring loci, the plural of locus, that arise from placing a condition on a complex numbers argument. Okay, let's begin with this example. This is asking us to sketch the set of complex numbers, each of whose argument is equal to minus 5 pi on 6. Okay, just have a think about that. And you might even venture to guess what such a sketch would look like. Every complex number whose argument is equal to minus 5 pi on 6. How might that sketch look? Okay, let's begin. You begin, as always, by drawing a complex plane or Argand diagram. Real z-axis in line with the positive x-axis, imaginary z-axis in line with the y. All right, so here's the recommendation. You find the radial line matching minus 5 pi on 6. So if you're working on a polar grid and every quadrant is split with 6 different radial lines, it's the 2 from the negative real axis that would match this, negative 5 pi and 6. And then what you need to do is draw a ray from the origin through that, along that radial line, if you wish. Have a think about it. It's made up of densely packed complex numbers, each of whom has an argument of minus 5 pi and 6. Okay, so it's a ray, it's not a line, it doesn't appear in the first quadrant, it appears only in that third quadrant because only those complex numbers along that radial line have an argument of minus 5 pi and 6. Does that make sense? I hope so. Now, what's a very important feature? Many students, according to Miss D, lost marks on the exam last year on this very simple feature, is that the ray is not defined at the origin. Have a close look. It's an open circle, actually, at the origin. Why would that be? Why would we draw a ray marking this condition on the argument, beginning with an open circle? If you've realized that because the complex number 0 plus 0i, the 0 complex number, it has no argument at all. So it doesn't make sense to include the point 0 plus 0i, or the origin, because it's not a complex number that meets the condition. In other words, it's not a complex number with an argument equal to minus 5 pi on 6. Okay, this leads us to the general concept of sketching an array on the complex plane. Anytime you're asked to sketch a set of complex numbers satisfying a condition on the argument of the complex number, then you're going to inevitably sketch a ray. Rays always have the feature of beginning at a fixed point. In this case, we're only looking at the origin, and that beginning of the ray must always start with an open circle. All right, this time we're placing a few more constraints on the set of complex numbers satisfying a particular argument value. Have a look at the diagram there. You can see every complex number along that blue line when, if you subtract A from the real Z component of it and B from the imaginary component, you translate that blue line back to the origin, and now it becomes a simple case of understanding how to sketch such a condition placed on the complex numbers. So it describes essentially the same thing as saying all complex numbers Z such that its argument is set to that particular value, theta, but just with translated, with involving a translation of A units in the positive real axis and B units in the positive imaginary axis. Now the ray, as always, starts with an open circle, but this time it's been translated to A comma B, or A plus BI, and that angle theta, the angle of the argument, is just made with the positive side of the horizontal line passing through B on the imaginary axis. So it's always measured in the positive X direction, if you will. Okay, have a go at sketching this set of complex numbers, this locus of complex numbers, under the given constraint on both Z and the resultant argument being equal to pi on 3. See if you can work out what to do. All right, you can return to the vodcast when you feel like you've successfully managed a sketch. Okay, I presume you've returned to the vodcast when you've already had a sketch. Now this is one recommendation. I probably wouldn't start with this myself, but the recommendation is to start with the basic sketch of arg z equals pi on 3, 60 degrees, draw the radial line, or get a sense of how the radial line will look. Now, what I recommend is actually locating the point, the open circle in which to begin your ray. So it might be handy if you actually rewrite it as z less a plus bi, and then immediately put an open circle on that a plus bi. So you can see there the open circle, the beginning of the ray starts at -4, 2. So that's what I would do. I'd then probably put a horizontal line in the positive real Z axis direction and mark in about 60 degrees from that, and then complete my sketch as follows. So that's how they've got it there. Marking in the dotted line parallel with the real Z axis, the angle measured from in the positive real Z direction, and that's pretty good. Open circle at -4, 2. Now you should probably continue on that ray through the imaginary Z axis, through the Y axis. But then the question is, how do you determine where the ray is crossing the Y axis or the imaginary axis? And of course, the way to do it, the way to work out where it is crossing that Y axis is via SOHCAHTOA. So you can just imagine picturing a right angle triangle, 60 degrees the internal angle, base length 4, you have to work out its height, add that height onto 2 as follows. Okay, so that's all I'm doing. That's what the ray would look like. Oops, I don't have an open circle. I should, of course. Hopefully you guys have. But it's a way to work out where it's crossing the y-axis. So 4 tan 60 is 4 root 3. And you've got some understanding, therefore, root 3 about 1.7, 4 lots of 1.7. 6.8 rounds up to 6.9, add 2 onto it, and so on and so forth. Okay, now what's important to note is the following. Now, you're never expected to label axial intercepts, so where your ray crosses the particular axis involved. However, you'll often be dealing with a scale that's already provided, and it will be expected that you know where it crosses roughly, between 1 and 2, between 8 and 9, or whatever the case may be. So you would be expected, given a grid or given a scale, to know where your ray does cross the real Z or imaginary Z axis. So please bear that in mind. SOHCAHTOA, that's all you need to do to work out that location. Okay, moving on from rays to other important matters. So it's nice to know there's a very simple, clean algebraic technique which will always exist for finding loci of complex numbers when one of the following two conditions are in place. So either it's explicitly appealing to the real Z function, where it maps the complex number to the real component, or the IMZ, the imaginary Z function, which maps the complex number to the multiple of I. So in either case, you end up with a real number. So when those two are in play on the condition, or the condition concerns modulus or distance, so modulus, then you can do the following. Wherever you see Z in the condition, replace it with X plus IY, and what you can do then is develop a rule between Y and X that can be sketched on the plane like a regular, ordinary garden variety Cartesian relationship involving Y and X. So how does it work? The key understandings are, of course, if it's real Z is mentioned, you can, wherever you see real Z, replace it with X. Wherever you see IMZ, imaginary function placed on Z, replace it with Y. And wherever you see mod of Z, you can replace it by the square root of the X values squared plus the Y values squared. Okay, let's see how that applies to these very simple cases. So let's have a look at this first locus of complex numbers on the complex plane. We're after all complex numbers, each of whom has the condition that its real component is equal to A. And of course, there they all are. So it's a straight line. It's a line parallel with the imaginary Z-axis running through A comma 0. Now, applying that technique of replacing Z plus equals X plus IY, we know what the real Z function does. It maps all complex numbers to its real component. So the set of all complex numbers whose real Z is equal to A is, of course, collapses down to simply the Cartesian rule X equals A. And we know how to sketch X equals A. It's that vertical line going through A comma 0 parallel with the Y-axis. Now, in a very analogous way, a very similar way, for us to collect the set of complex numbers, each of whom has an imaginary value of B. So applying the IM function to our complex rule, X plus IY, it takes out those multiples of I and gives you the value Y. So this idea of collecting all complex numbers whose imaginary component is equal to B really is reducible to the Cartesian relationship Y equals B. And that's, of course, just the horizontal line going through 0 comma B. Pretty simple, really. All right, folks, I'd like you to have a go at those 4 simple sketches. Each of them involves a straight line parallel with one of the 2 axes. Have a go now and then resume the podcast when you're ready. Okay, I presume you're back now after having a go at those 4 sketches. Let's consider the first 2. They're pretty basic, aren't they? So clearly, if I can replace Z, real Z with X, it's just simply the vertical line going through 3.5 comma 0. Makes perfect sense. Each of the points, each of the complex numbers that make up that vertical line, each have a real component of 3.5. Similarly, if I think of all the complex numbers whose imaginary component is X equal to minus 2, it's equal to the flat or horizontal line going through 0 comma minus 2, whose Cartesian equivalent rule would be y equals minus 2. So it makes sense. Any complex number along that straight line has an imaginary component equal to minus 2. So it'd be something minus 2i in Cartesian form. What about the other two? Now clearly we'd know what real z is equal to 1. It'd be a vertical line going through 1, 0 parallel with the y-axis. Now what I'm doing though is applying it to not just complex numbers but to complex numbers which have 2 subtracted from their real component and 3 added onto their imaginary component. Now adding 3 into the imaginary component won't change which set of complex numbers I draw from that particular condition, but certainly subtracting 2 from it, because effectively what I'm doing is I'm taking any complex number whose real component is equal to 3, and once I subtract 2 from the real and add 3 to the imaginary, which has nothing, I'm left with all complex numbers whose real component is equal to 1. All right, so it makes perfect sense from the sense of translations. Now, of course, I could just replace z with x plus iy, collecting my real, collecting my imaginary. The real z function applied to it leaves me with x plus x minus 2. We're setting that equal to 1, transposing. We've got the Cartesian relationship x equals 3. So you could walk through that process quite conveniently to come up with the right sketch. Now, for the set of all complex numbers whose imaginary component, when I subtract 5, all complex numbers such that when I subtract 5i from their rule, I'm left with an imaginary component of minus 3. What set of complex numbers would that be? Well, as you can imagine, if I set my imaginary bar down at minus 3, add 5 onto that, it's all of those complex numbers. So each of those complex numbers, something plus 2i, when I subtract 5i from each of those, I have a complex number with an imaginary component of minus 3. Again, you can walk through the algebra, replacing z with x plus iy, collecting real, collecting imaginary, applying the imaginary component, imaginary function to it. I'm left with the Cartesian relationship y minus 5 is equal to minus 3, adding 5, I've got the Cartesian relationship y equals positive 2, an easy sketch indeed. Of course, with this in mind, I can sketch lines not just parallel to one axis or the other, I can sketch any straight line. So notice we've got lines and rays, they're not the same thing. I'll always get a ray when I place a condition on the argument of complex numbers. I'll always get a line when I place the real z or imaginary z functions onto the complex numbers, and or imaginary z functions onto the complex numbers. So look, it's really a simple rule of thumb. Wherever you see real z, replace it with x. Wherever you see im z, replace it with y. So effectively, in that condition that you see, the set of all complex numbers where 2 times the real component minus 3 times the imaginary component is equal to 6 is effectively just the straight line with the simple rule 2x minus 3y is equal to 6. That is equivalent to that Cartesian rule, which you can sketch quite neatly on the plane. Okay, a lot of the loci of complex numbers you'll be asked to sketch on the plane result from a condition placed on distance or moduli involving complex numbers. Now, in order to get an intuitive sense for what this means, it's important that you appreciate when I take the mod of the difference between any two complex numbers, z1 minus z2 mod, I've got the distance. It's a way of measuring the distance between those two complex numbers. Now, of course, the order doesn't matter because the modulus removes any negativity between the two. So z1 minus z2, or equivalently z2 minus z1, will give us the distance between any two complex numbers, z1 and z2, on the plane. That's an important concept for where we're going. Let's just flesh that out a bit. So let's think about it in terms of our vector understanding of complex numbers, adding and subtracting them on the plane. So there's, of course, z1 plus z2, represented as the head-to-tail vector resolution of z1 plus z2. thinking of them as vectors, as position vectors. Now, if we think of negative z2 and put it onto the head of z1, the difference between z1 and z2 is given by that vector, and the magnitude of that gives you the distance between those 2 points, those two numbers, z1 and z2, on the complex plane. Okay, so there it is. All right, so that's an important thing to just be aware of. It gives you a sense of intuition for what may be happening in a particular problem or sketch. Okay, have a look at this particular condition placed upon Z. We need to sketch all the complex numbers that satisfy this particular condition. What do you think it's really being asked from a geometric point of view, especially in light of what was discussed in the previous slide? So that's what I want you to think about. What condition is it really being asked upon Z? Now, it might be helpful to re-describe it as follows in terms of difference between our arbitrary Z and particular points. So have a think again. Now, what geometrically this is really being asked to describe. What set of complex numbers would match this condition? Okay, if you were thinking about it in these terms, then you'd be right. So what we need to find is the set of all complex numbers whose difference in distance between minus 4 plus 3i is equal to its distance to minus 2 plus 3i. Does that make sense? It describes a set of all complex numbers whose distances from minus 4 plus 3i on the plane is equal to its distance from minus 2 plus 3i on the plane. Have a think about where those 2 points lie on the plane. Obviously, they're at the same y value. They have the same imaginary component. So what do you think would be all complex numbers to satisfy that condition? If you're thinking about a vertical line through x equals minus 3, so any complex number with a real component of minus 3, then you'd be right. So as you can see, each complex number along that line is equidistant to minus 4 plus 3i and minus 2 plus 3i. Interesting. Now, even if you didn't get that geometrical intuition, you can always do the simple algebraic trick of replacing z with x plus iy in the rule. Let's just walk our way through this, shall we? Okay, we collect our real parts and our imaginary parts. We apply the definition of a modulus. It's the sum of the real components and imaginary components squared and then the square root of that. Squaring both sides, we can remove that. We can eliminate y minus 3 all squared from both sides and then square the perfect squares, x plus 4 and x plus 2 all squared, leading to that. You can see x squared being able to be eliminated at that point, moving the 4x across, moving the 16 across, and solving for x, we get x equals minus 3, a Cartesian description of that locus of complex numbers. Okay, here's another example quite similar to the last one. And in fact, it is so similar, deliberately similar. I wonder if you can see a link that we can make between that, the previous one and this one. Now, of course, we could just replace z with x plus iy, blindly run through the routine, collect your real, collect your imaginary, square and sum, etc., 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 and get to the right answer. But there is, in fact, a neater way you can go about that. A way that you can pick up if you see the geometric constraint being placed upon this condition on Z. So if we write it in that fashion now, have it related if you can to that previous example. So we're talking about the set of all complex numbers whose distance to 2 plus 3i is equal to its distance to minus 1 plus 4i. In other words, the set of all points whose distance from 2, 3 is equal to its distance from minus 1, 4i. Is there something from our linear algebra understanding that can help us in this context? I mean, what is really being asked to sketch here? So if you were thinking in terms of the perpendicular bisector, equivalent to that last particular example, between the points 2, 3 and minus 1, 4, then you'd be spot on. So let's just see how that would work using our understanding of linear algebra and coordinate geometry. So if these are the 2 points in question, then of course we can work out the gradient of the line segment connecting those 2 points. It turns out to be minus 1/3. So the gradient of the line perpendicular to it is its negative reciprocal 3. The midpoint of those 2 points, 2 plus minus 1 over 2, and 3 plus 4 over 2 leads to 1/2, 3.5, or 7/2. Whacking it into left, our linear equation finder, and expanding, collecting like terms, leads to that simple Cartesian relationship. Now that's a completely valid way and a neat way to go about working out the locus of complex numbers, the Cartesian equation for it, for this particular condition on Z. Now, why don't you have a go at replacing Z plus equals X plus IY now, sub it into the rule above and see if you can too get through Y equals 3x plus 2. I'll give you a moment to have a crack at that now. Okay, if you're back, resumed our vodcast, then I presume you've actually had a go at it and you've gone through working out something like this, replacing Z with X plus IY on the left, Z plus XY on the right, collecting our real, collecting imaginary, squaring, summing, squaring both sides, expanding all perfect squares, removing x squareds and y squareds on both sides, leading to just linear combinations of x's and y's, collecting those, and of course we get down to the same answer. So if this was a question on an exam, you had to come up with the Cartesian rule for the locus of complex numbers satisfying that condition. It's your choice. How would you prefer to work under exam conditions? Using our linear relations and skills on coordinate geometry, or running through the algebraic routine? It'd be up to you. Okay, here's a new one for you to have a look at. You might be asked to sketch something like that, the set of complex numbers satisfying that particular condition. Now, sometimes, and we'll look at patterns involved in these sort of questions where you can immediately know what sort of sketch you're looking for. But in this particular instance, and in any instance when you're not overly sure, just run through the algebraic routine, replacing Z with its Cartesian generalization, X plus IY, and you end up with a rule that you can sketch, a familiar rule that you can sketch involving X's and Y's. So I'd like you to have a go at that now and see what you come up with. Okay, you're back to the vodcast. I presume you've had a go and you've got an answer you'd like to see how you've gone on. So let's run through the routine. Replacing Z with X plus IY, the generalized Cartesian expression of a complex number, leads to that, collecting your real and imaginary components, taking the sum of the squares, square root, and then in one foul swoop we'll square both sides as well. It leads to that particular expression. Now you might pick up that we're not going to drop our x squares and y squares terms in this particular case. Let's just expand, and then we can collect our x squares and y squares on one side of the equation. And then why not let's perform some completing the square to both sides. So you can see where we might be going at this particular point, adding 4 with the x terms and 1 with the y terms, and adding those values to the right as well to keep things balanced, leads us to this particular rule. Aha! That's an easily recognizable form as a circle with center 2, 1 and of radius 2. Interesting, it's not something that you would have naturally thought of with the original expression of the condition on Z. All right, so in that previous example, we started out with a condition on Z for which we have to sketch, and it turned out to have a circular locus of points. So it wasn't entirely obvious, it wasn't clear at all from the way it was initially set up that it would indeed lead to a circle. So let's have a look at some rules that are more obviously generate circles. So here's a standard definition of what a circle is, or a set of points that make up a circle. So it's a set of all points that are a fixed distance from a single focal point. So what gives rise to distance under conditions placed on Z? And what would that focal point be represented in such a condition placed on Z? I want you to think about how a more direct and more obvious way in which we could come up with a circular locus of complex numbers based on a condition. Okay, so if you're thinking along these lines, then well done to you. So if we collect the set of complex numbers whose moduli is fixed at R, then what are we doing? We're defining a circle of points of radius R and center the origin. So each of those complex numbers satisfies that very simple condition, and that's indeed clearly supported by our routine of replacing Z with X plus IY. As you can see, putting that into the rule mod Z leads to the square root of x squared plus y squared equals r, which is x squared plus y squared equals r squared, which is, as we know, the Cartesian rule for a circle centered at the origin of radius r. Okay, it's a very small step to talk about circles centered at the origin of radius r to circles with some other focus point. So in other words, a translation of that situation to some other point a comma b. So if you have a think about this rule for a moment, the set of all complex numbers whose distance between it and the point a comma b, or a plus bi, is fixed at r, of course naturally describes a circle of radius r and center a plus bi. Okay, I'd like you to have a go at sketching these critters on the complex plane. So pause your vodcast and then resume when you're ready to check your answers. Okay, you've returned after having a go at them yourselves, and clearly what we're describing, the set of all complex numbers whose distance to -1 is fixed at 2, is nothing other than a circle of complex numbers, center -1, comma 0, and radius 2. Similarly, for the second one, if I think of it as Z take 2 minus 3i, so I just have to think of it, the new center of the circle being fixed at 2, comma -3, and we're talking about the set of all complex numbers whose distance from 2, comma -3 is set at 3. So in other words, a circle of radius 3 with center 2, comma -3. So again, like with all of these questions involving moduli or real and imaginary functions, it can be validated using the Cartesian methods, replacing Z with the generalized x plus iy. Let's have a look at that particular example. The modulus of x minus 2 plus y plus 3i is set at 3. So that's using the definition of modulus. That's of course leading to the Cartesian rule for a circle of radius 3 centered at 2, comma -3, as we'd suspect it would. Okay, so we've seen circles emerge in two different ways. So one from a more direct understanding as a set of all points of fixed distance from a focal point or center, and that was in the ways we were just practicing previously. And prior to that, I threw out a condition that did lead to a circular locus of complex numbers, but it wasn't quite obvious that it would lead to such an endpoint. It wasn't until we did our replacements of x plus iy that such a locus emerged. Now here's another one. There's in fact a third variety of condition on Z that leads to a circular locus of complex numbers. I want you to have a look at it now. So Z minus a particular complex number, 1 minus 2i, times by its conjugate minus the conjugate of that value. 1 plus 2i is equal to a set value. Now, that in fact leads to a circular locus of complex numbers. I just want you to spend a moment replacing Z with x plus iy. and see for yourselves how this, well, that a circle emerges, and maybe just think about why it does in this particular setting, and why it'll, and see if you can generalize to a general form of conditions of this nature that lead to circulars with fixed radii and fixed centers. So anyway, have a go. Z equals x plus iy, make that replacement and see what comes your way, and then we'll discuss it in a moment. Okay, you're back to the vodcast, so you're ready to go. Z equals x plus iy. Let's make those replacements in the rule. So that leads to a real and imaginary component on the left-hand factor. Now, of course, it's z bar. I'm replacing z with x plus iy under the guise of z bar, its conjugate. So I'm replacing, so its replacements become x minus iy. And when I collect real and imaginary components on the right-hand multiplier, that's what it looks like, equals to 4. Now, straight away, you might pick up, in fact, that what we're doing is multiplying generalized complex numbers in conjugate form. You've got the same real component, you've got the same multiple of I, but one's positive and one's negative. So if you're onto it, you could have gone straight into the form of the answer, x minus 1 squared plus y plus 2 squared is equal to 4, or you would have arrived at it via cancelling of terms. So you can see for yourself, it leads to a circle of radius 2, center 1, negative 2. Now, let's think more generally. So suppose we're given something of this particular form. Oh, I'm missing a bracket there. I'm not going to replace it now. I'll replace it later. Z minus a complex number, bracket, times Z bar minus the conjugate of that complex number is equal to R squared. In fact, it always produces a circle of radius R with center A, B, or complex center A plus BI. Now, have a think about why. Have a think about why. All right, so if we replace Z with x plus iy in both instances, you can see that you're going to always get this situation of a generalized complex number, x minus a real, y minus b imaginary, times by its conjugate, which of course will always lead to x minus a squared plus y minus b squared. And of course, if that's set to r squared, it's describing in Cartesian rule a generalized circle of radius r and center a, b. Okay, let's summarize this session quite quickly, and I'll give you a handout that alludes to this particular summary. So we began our session by looking at conditions on the argument of z, and that always will produce array. Array distinctively has a fixed starting point drawn as an open circle, and it heads off in the direction of the argument, more drawn anti-clockwise from the positive real z axis. So of course, if it's standard, as you can see above, it's the ray begins at the origin, otherwise it's translated to the position A, B. We then moved on to straight lines. So straight lines would be of the form combinations of real z and imaginary z, or in fact, of course, it could be the perpendicular bisector between 2 points, A1, B1 and A2, B2. Now, I presented 2 different ways you might go about coming up with the Cartesian rule of that perpendicular bisector, replacing z with x plus iy, which is the usual stock standard way. But of course, if you're right onto it, you can just work out the midpoint between the two, the negative reciprocal of the line segment connecting those 2 points, and using your skills in linear relations, come up with the rule for the locus of points. Okay, now the third type of object you'll be sketching in the complex plane are circles, and these are the 3 generalized ways in which circles emerge. So you've got z minus bi is equal to r, and that's, to me, that's just the most intuitive and obvious way in which a circle can be described upon a condition, with a condition upon complex numbers. So it's clearly stating a circle of radius r of center AB, because after all, what is modulus? It's talking about the distance between complex numbers and that particular point A comma B being fixed at R. Now, this is the one we threw your way and said replace Z with X plus IY and see what emerges, and lo and behold, a circle did emerge. In that particular example we use, K was set at root 2. Now it could be either in that form or in the form you see in brackets. Provided K is anything but 1, it will always produce a circle. Now, I'm not imposing anything about its center or its radius based on the general form of the condition on Z, but it will always produce a circle provided that K value is not equal to 1. Of course, when it is equal to 1, it defaults to that perpendicular bisector condition discussed above. Now here's that third case of a circle, and this is really handy to know all these shortcuts when you're dealing with multiple choice questions. You can hone in on an answer very, very quickly. If it's of the form Z minus alpha times Z bar minus alpha bar is equal to some R squared, you know it's also a circle of center alpha and radius R. Now just a little bit more on that. So if we just expand what alpha could be is A plus BI, we know, well, if A plus BI was equal to 0, we're obviously talking about the very particular example of a circle of radius R, center at the origin, and it just collapses to, of course, Z times Z bar, which is mod Z squared equals R squared, which of course collapses to mod Z is equal to R, and we're returning to our initial and most direct understanding of what a circle is when centered at the origin. Now, if A is equal to 0, so in other words, if the real component is set to 0, the relationship reduces to that form, and so you know it's a circle centered at 0 comma B of radius R. And of course, if the imaginary component is equal to 0, then it's of the form you can see down there in the bottom right hand corner. So it's a circle of radius R centered at A comma B. And notice, of course, minus A, it doesn't appear to be of the form, the most generalized form, but of course, when the real component is A and the imaginary component is 0, then it has the same real component in both of its factors. That's it for now. Use that handout that I'm going to give you summarizing all of this. Stick it into your bound set of notes. It's an incredibly useful summary that could lead you very, very quickly to a solution in a multiple choice setting. That's it for now. It's time to practice problems in the final exercise and then review your work in complex numbers. That's it for now, folks. See you later.